So this law says the relationship between concentration and partial pressure in a solution. So we're going to be looking at solutions, why we care about this. We won't be looking at Coca-Cola more than this lecture. We care about solutions because that's our plasma, right? Our blood plasma is a solution, and it's an aqueous solution specifically. So how a gas dissolves in water is going to be important. Gases can dissolve, have different solubilities. So that's why this is going to matter. So a gas will dissolve in a liquid in proportion to its partial pressure. So the partial pressure of a gas will contribute to its dissolving, but so does solubility. So for those of you who like equations, you can have an equation. You don't need to know this, but if you're someone, some of you do actually, believe it or not, if you're someone who doesn't, some of your classmates do, concentration is equal to solubility times pressure. This is concentration of a gas. And we're talking about in solution, is going to be proportional both to K, which is a characteristic of the gas itself. Also dependent on temperature though, as you know about, solubility of the gas. So it's a property of the gas, is dependent on temperature and the solvent as well. We're not going to go into that more. We would look at it as varying depending on the gas. So oxygen has a different solubility than carbon dioxide, given whatever other conditions we have. P is our partial pressure. So the concentration of a gas is going to depend on solubility and the temperature. Solubility and partial pressure. Every gas has a different solubility. So carbon dioxide dissolves easily. It has a high solubility. O2 has a lower. This is where the soda comes in. Carbonated soda has a lot of carbon dioxide dissolved into the liquid. That's what carbonation is. Carbon dioxide is pumped in so that it's into the liquid. And it's kind of for fun, but it demonstrates this nicely. Let me show you what happens here. So when you open a can of soda, you're releasing pressure. This is what I showed you before. There's a lot of carbon dioxide dissolved in the soda. That's because CO2 has a high solubility. So you can have a lot of it in there. It's gonna be dissolved in there. When you release this pressure, because the partial pressure of carbon dioxide is now lower outside of the can, it's gonna come out it's gonna be released. So PCO2 in the atmosphere, you already know is really low. What we say it was, 0.03, I think. It's definitely lower than in here. It's actually pretty darn high in here, right? Because we packed this thing full of carbon dioxide. And that's what the bubbling of your carbonation is. And then your drink will become flat if you leave it out because it reaches equilibrium. So again, this is actually an example of Henry's law. So a soda becoming flat is carbon dioxide reaching partial pressure, reaching equilibrium with the atmosphere. You can now tell your friends that when your drink gets flat. Equilibrium. So when you have a flat soda, the partial pressure of carbon dioxide is actually at that point equal inside that can of soda and outside. Pretty low in that case. Why does this matter? So again, let's write this down. The concentration of a gas in solution is proportional to its partial pressure. And that would be partial pressure, in this case, like above the solution. So let's just say that's here. So above, or next to where the solution is. Here, we've got gases above the solution. What's going to happen to this gas? I have PO2 listed for you here. What's going to happen if we allow this gas to enter solution? Let's say that we had a lid over it and then we opened up the container. It's going to diffuse into that solution. Until when? What will the partial pressure of this be? PO2 question mark. Well, it's going to be equilibrium, right? This is equilibrium. However, is concentration equal in the two? No, not if this is oxygen. Concentration will not necessarily correlate with partial pressure for several reasons. The solubility of the gas, depending on the solution. So again, this is water. So concentration here will be lower because oxygen solubility is low in water. And this is why we look at partial pressure gradients, not concentration gradients of gases. Because when we're looking at solutions, solubility is a significant factor. So Henry's law is going to underlie principle of diffusion of gases in the capillaries and alveoli, and between the capillaries and interstitial fluid by the cells, because we're looking at gases in solution. We've got to look at, and really it's emphasizing why we look at partial pressure gradients. The other important thing is that the solubility of carbon dioxide and oxygen are different. Oxygen does not diffuse well in aqueous solutions. That's going to be why we have hemoglobin.